Section 4.5 talks about first-order linear differential equations. These are differential equations in the standard form y prime plus p of xy equals q of x. The dependent variable are y and its derivative are first degree, while the coefficients that we see here only depend on the independent variable, which is x. To solve these linear differential equations, we would first write the equation in standard form. This is the first thing that you check because sometimes the standard form isn't obvious and you have to do a little bit of manipulation to get it into this form. The next step is to find the integrating factor, your I of x, or in some books like OpenStax, they use mu of x, and some differential equations, professors also prefer to use mu. But they're the same thing. And to find the integrating factor, it is just e to the power of p of x dx. Then you would multiply both the right and the left side of the equation in standard form by I of x, and consider rewriting the equation as the derivative of the integrating factor times y. The integrating factor times y is the same as the integrating factor times q of x. And we'll notice in our first example that we're just essentially rewriting the left side in this nature, which is undoing the product rule. Because what's happening is that we see that the left side eventually looks like a derivative. And that derivative is in the form of a product rule. So to find the original function, we're basically undoing the product rule because we want to find the original function and we want to integrate. That brings us to step 5, integrating both sides of the equation, and step 6, solving for our y. So we call I of x the integrating factor because its presence is what makes the left side integrable. When the left side has the form I of x times y prime plus p of xy, when we distribute the I of x, we get I of x y prime plus I of x p of xy. But the left side needs to ultimately be the derivative of the product. And we see here that this is essentially a product rule where f equals I of x and g equals y. So we have f g prime plus f prime g. But what does this have to do with p of x? Why is there a p of x in the integration factor? Well, if you set both of these equal and you subtract or cancel out I of x y prime because it's on both sides, you're left with I of x p of xy equals I prime of xy. We're going to cancel out the y's again since they're on both sides. And we see that we end up with a separable differential equation, which we can just integrate on both sides. Now, if we want the I of x all by itself, we just exponentiate both sides and we get, voila, I of x equals e to the power of the integral of p of x dx. And we will be using this integrating factor to solve our first order linear ODEs. All of this will make a lot more sense when you see the first example. Okay, so let's follow the 6-step procedure for example 1. First, is this equation in standard form? Is y prime plus y equals 1 in standard form? And as a reminder, the standard form is y prime plus p of xy equals q of x. So we see that this is already in our standard form, but you might be thinking, wait, I don't see any p of x's or q of x's. There's no x here. So you might be thinking, wait, how is this in standard form if we don't have any x's? Well, it turns out you do. Well, and you might be thinking, why is this in standard form if we don't have any x's? Well, the function p of x just equals 1 because this is our y prime, this is our p of x, this is our y, and this is our q of x. And that brings us to step 2. The integrating factor equals e to the power of the integral of p of x dx. And we already saw here from step 1 that our p of x is just 1. And that makes this very nice because the integral of 1 dx is just x. And that means our integration factor, or integrating factor, is e to the x. Now, for step 3, we will multiply everybody by the integrating factor. And let me color code this, e to the x. So if we multiply both the left and the right side by our integrating factor, this is what we get. Now, what do you notice about the left side? This is a product rule for derivatives. This is your f g prime plus your f prime g. And remember, we have to eventually integrate both sides. So if this is the derivative, we're trying to find the original function that generated this product rule. So we know that the original function that gave us this product rule has to be f times g, right? Because this is our f and this is our g. So this brings us to step 4. The derivative of our original function, f times g, let me color code this, our f and our g equals e to the x. For step 5, we will integrate both sides. And by the fundamental theorem of calculus part 1, we know that this cancels and we're just left with e to the x times y equals e to the x plus c. This is our implicit answer. If we want to get y all by itself, we just have to do one last step. And that is divide everybody by e to the x. So I'm just going to divide everybody by e to the x. To get y all by itself. We get y equals 1 plus, since we have e to the x in the denominator, I can just rewrite that as c times e to the negative x. This is our explicit answer. Ooh, I'm not sure how that integral got there. Let me just erase that. And I wanted to make one more note up here for number 4. The derivative of the e to the x. Ooh, I don't feel like I need to make that note. This is just the derivative of the integrating factor times y. And this was what we saw earlier here. Our integrating factor in this case was just e to the x. Okay, so example 1, pretty good, pretty simple. Let's move on to number 2. Right off the bat, I see that we're given an initial condition, which means that we want to find c. And I also noticed that, ooh, okay, this dy dx, or this y prime, isn't by itself, because we want it to get it into the form of y prime plus p of xy equals q of x. So we need to do a little bit of an extra step, but that's not bad. We're just going to divide everybody by cosine squared x. So we get that dy dx plus y over cosine squared x equals 1 over cosine squared x. And what is 1 over cosine squared x? That is the same as secant squared x. So we have y prime plus secant squared x times y equals secant squared x. Now, is this in our standard form? Yes, it is. Because we have our y, we have our p of x, we have our q of x. To find our integration factor, we have I of x equals e to the power of p of x dx, which means we're integrating secant squared x dx. The integral of secant squared x is just tan x. So this turns out to be our integrating factor. Step 3, multiply everybody by the integration factor. So we have e to the tan x y prime plus secant squared x y equals e to the tan x secant squared x. So I just took this and multiplied both the left and the right side by the integration factor. Now, what we'll notice, just like example 1, after we distribute the integrating factor, we get e to the tan x y prime plus e to the tan x times secant squared x y equals e to the tan x secant squared x. And again, this is another product rule. So we notice that f equals e to the tan x and g equals y, because we have f g prime plus this entire thing is our f prime because of chain rule, and then this is our g. Because f prime equals e to the tan x times secant squared x. We have to take the derivative of the outer and the inner. Good old chain rule. All right, for step 4, it is time to put it in the form of the original function. We're just trying to find our f and our g. So our f and g corresponds to e to the tan x times y. And that equals e to the tan x times secant squared x. We can finally integrate both sides. And I'm running out of room here, so I'm just going to make everything a little bit smaller. And we're left with e to the tan xy equals the integral of e to the tan x secant squared x dx. Here we can just do a really simple u sub and let u equal tan x and du equal secant squared x dx to integrate this. I'll do that off to the side. We get integral of e to the u du equals e to the u. When we back sub, we get that e to the u equals e to the tan x. Have our plus c. So that is our integral on the right side. And for number 6, we just have to get y all by its lonesome. So again, divide everybody by e to the tan x, and we get y equals 1 plus c over e to the tan x. This is our explicit answer. But wait, unlike the first one, we're not done because we were given a piece of information in the beginning of the problem. Don't know why this box moved, but let's put it back because it gave us our initial condition that y of 0 equals -3, which allows us to find c. So using our initial condition, using y of 0 equals -3, find c. -3 equals 1 plus c over e to the tan 0. Because in this case, x is 0. So we get -3 equals 1 plus c over 1, and c equals -4. So the last step that we have to do is just to replace this guy with -4. And a nicer way to write that is to put a minus sign over here and a 4 up here. And we're all done. This is our particular solution. And that answers the question. And on to our last example, example 3. Now, right off the bat, this does not look like it's in standard form, right? Because first of all, the differentials are not together. We don't have the dy over dx. And we also have to get y prime all by itself. But my first step is to actually have dy over dx. So what I'm going to do is move the dx over to the other side. And I get 1 plus x squared dy equals -xy plus x cubed plus x dx. And I'm going to divide both sides by dx. If I divide both sides by dx, I get 1 plus x squared dy over dx equals -xy plus x cubed plus x. And now I want to distribute this negative sign to everybody here. So let's go ahead and do that. 1 plus x squared dy dx equals -xy minus x cubed minus x. So now I'm going to move the -xy over to the other side. And the reason I'm doing this is because if you recall our standard form, I'll write it again up here. We have y prime plus P of xy equals Q of x. So on the right side, we want to just have all x's. Now it's finally time to divide everybody by the pesky 1 plus x squared because we want dy dx to be by itself. So we have dy dx plus xy over 1 plus x squared equals negative x cubed minus x over 1 plus x squared. And let's rewrite dy dx as y prime plus x over 1 plus x squared y. This way we can see our p of x very clearly equals. Now, I am going to factor out a negative x in the numerator because that leaves us with x squared plus 1, and voila, doesn't that cancel with the bottom? How beautiful. So let's rewrite what we have. And this is in standard form. Finally, that was quite some work just to get to step 1. Let me make this smaller so we have room to actually do the problem. Okay, 1, get it into standard form, done. Step 2, let's find I of x. And I of x equals e to the integral of x over 1 plus x squared dx. Because this guy, this is our p of x. So this is a very, very simple u sub. Not bad at all. We let u equal 1 plus x squared and du equals 2x dx. That means du over 2 equals x dx. And when we integrate this, we'll get e to the 1/2 integral of 1 over u du, which equals e to the 1/2 ln of u. And remember to back sub into variable x. That equals e to the 1/2 ln of 1 plus x squared. But we're not quite done yet because we can simplify this. E to the 1/2 ln of 1 plus x squared is the same as e to the ln of 1 plus x squared to the power of 1/2. And now you can go ahead and cancel. You have to bring this 1/2 in first before you cancel out the e to the ln. So this equals 1 plus x squared to the power of 1/2, and let's rewrite this plus the square root of 1 plus x squared. As you can see, this one is a little bit more involved. Step 3, let's multiply everybody by the integration factor. And we get step 4. Notice that this is a product rule, and that means we can rewrite it as d dx of f times g. So we have 1 plus x squared times y. And this is our f. And this is our g. Equals negative x times the square root of 1 plus x squared. Step 5, integrate both sides. I am too lazy to write all this again, so I'm just going to copy and paste it. And I'm just going to bring this negative out to the front instead. On the left side, I will have 1 plus square root of x squared times y. And on the right side, we'll do a simple u sub and let u equal 1 plus x squared. So du over 2 equals x dx. Negative 1/2, I'm just pulling out the du over 2 is 1/2. Integral of u to the 1/2 du. And that equals negative 1/2 times u 2/3 u to the 3/2 plus c. Cancel, cancel. And remember to back sub. So this is negative 1/3 1 plus x squared to the 3/2 plus c. To get, this is our implicit answer. And we get that y equals negative 1/3 1 plus x squared to the 3/2 divided by 1 plus x squared to the 1/2 plus c over the square root of 1 plus x squared. The reason I rewrote it as 1 plus x squared to the 1/2 is just so that you can see that 3/2 minus 1/2 clear in the exponents. So this turns into y equals negative 1/3 1 plus x squared plus c over the square root of 1 plus x squared. This is our final explicit answer. Will it make a box? It did not make a box. That's fine. So that was quite a bit of work for just this one problem. But we're finally done, and that concludes differential equations for Calc 2.